Hello everyone. In this AV, we would be talking about the remaining portions of the chapter Flow of Liquids. In the previous AV, we had already talked about the Stokes law, which states that the force over a liquid is nothing but given by 6 pi eta r v. Now we will continue our discussion from here. Now we will find out what are the factors on which the volume of liquid flowing per second through a pipe depends on. So the first thing on which the volume of liquid flowing through the pipe depends is viscosity. This is the first thing. The second thing on which the volume of liquid flowing through a pipe depends is the radius of the pipe. And finally, the third thing on which the volume of the liquid flowing through the pipe depends is the pressure per unit length. That is the pressure gradient. Now, the rate of discharge through a pipe, that is Q, is given as K P r to the power 4 upon eta L, where Q is the rate of discharge, K is a constant, P upon L is the pressure gradient, R is the radius of the pipe, and eta is the coefficient of viscosity. Now, by experiments, we find that the constant of proportionality K has the value pi by 8. So this whole equation can be rewritten as Q is equal to, instead of K, we are writing pi by 8, and rest of the quantities remain the same, that is P r to the power 4 eta L. Now this relation, which tells us about the rate of discharge of the liquid through the pipe, is known as Poiseuille's relation. Poiseuille. Poiseuille relation. This is also a law, and it helps us to find out the rate of discharge through the pipe, and it helps us to determine the viscosity of a liquid. Now if we rearrange this term, what we can write it as is Q is equal to P upon, rest everything we are taking it down, so we have 8 eta L, and pi r to the power 4, we are writing it like this. So after this, if we compare it with the equation of current electricity, that is I is given as V upon R, that is voltage upon resistance, then we can say that this resistance is this quantity, that is R is equal to 8 eta L upon pi r to the power 4. Now this R here is known as the viscous resistance. Viscous resistance. So with this formula we can find the viscosity or the viscous resistance of a liquid. So from this formula we know that the viscous resistance is directly proportional to L. That means the length of the pipe. So if the length of the pipe is more, viscosity or viscous resistance will be more. It is also directly proportional to the viscosity of the, coefficient of the viscosity of the liquid, and it is inversely proportional to the radius of the pipe. So if the radius of the pipe is more, the viscous resistance will be less, and this leads us to the principle of continuity. principle of continuity tells us that suppose we have a pipe where suppose the fluid or the liquid is flowing from. So we find that here this is the inlet and this is the outlet. So automatically area 1 is greater than area 2. So suppose we have V1 as the velocity at the inlet and V2 is the velocity at the outlet. So what we find is the amount of water entering at the input will be same at the output also. That means area multiplied by volume will be constant. How can we prove it? Now let's assume that rho is the density of the liquid which is flowing inside. Then the mass, if I have to find out the volume of the liquid in 1 second entering at, let's say, x, and this is y. So volume of the liquid entering at the end x will be area multiplied by the velocity, that is a1 into v1. And if I have to find out the mass of the liquid at x or entering at x, then volume multiplied by the density will give me the mass. So rho a1 into v1. Now similarly, the mass of the liquid coming out from area a2 or at the end y will be given as a2 multiplied by v2. And if I have to find out the total mass, then it would be rho multiplied by a2 into v2. So this is my mass of liquid at y. Now the liquid which enters at one end, that is from x, must also leave at the other. So both the masses are equal. So if both the masses are equal, we can equate it together. That is rho a1 multiplied by v1 is equal to rho a2 multiplied by v2. If that is the case, rho and rho can be cancelled out, and this equation can be rewritten as a multiplied by v, that is area multiplied by the velocity, is a constant. And this is what is known as the principle of continuity. It states that when an incompressible and non-viscous liquid flows in streamlined motion through a tube of non-uniform cross section, here we find that the tube is non-uniform, then the product of area of cross section and the velocity of flow is the same at every point in the tube. Now this principle of continuity is responsible for the increase in velocity of water coming out through a pipe, and you all must have observed it while watering your plants in the garden. If we want, suppose you have the pipe and you want the water to reach maximum distance, so what we do is we make the opening slightly narrowed so that the velocity of the water coming out from the pipe increases. That is what we do. We apply the principle of continuity. That means we know that a into v is a constant, so what we do is we are decreasing the area of the outlet of the pipe, so automatically the velocity of the water coming out of the pipe increases, and that's how it covers a larger distance. Now when a liquid is flowing, then we have three types of energies of that liquid. First one is the pressure energy, generally denoted as P. The second type of energy of a flowing liquid is the kinetic energy. We have learned that kinetic energy is half mv square. In case of liquid, we write it as half rho v square. And finally, the third type of energy possessed by a flowing liquid is the potential energy. And that is denoted as rho g h, because this is the height denoted as h and g is the acceleration. So at times, instead of this g, you might also come across a, that is acceleration due to gravity, or g. Both represent the same thing. Now if we combine all three, then the sum of pressure energy plus the kinetic energy plus the potential energy is always a constant for a flowing liquid, and this is what is known as the famous and important Bernoulli's theorem or Bernoulli's principle. Now the statement is given as, when an incompressible and non-viscous fluid flows in a streamlined motion from one place to another, then at every point of its path, the total energy per unit volume, that is the pressure energy, the sum of the pressure energy, the kinetic energy and the potential energy, will always remain constant. And this is Bernoulli's principle, and we can also say that Bernoulli's principle or Bernoulli's theorem is in one way the principle of conservation of energy for a flowing liquid or a flowing fluid. So now to prove the Bernoulli's theorem, let's look at this picture. Here we have a pipe XY which is non-uniform, and we assume that an incompressible and non-viscous liquid is flowing in a streamlined motion through this non-uniform cross section of the pipe. We have the area A1 and at the end X and the area A2 at the end Y. Obviously area A1 is greater than area A2, so automatically the velocity of the liquid at the end X is V1, which is lesser than the velocity at the end Y because the area is smaller. We also assume that P1 is the pressure at the end X and P2 is the pressure at the end Y, and end X is at a height of H1 and end Y is at a height of H2. So to prove the Bernoulli's theorem, first we find out the work done. Now here we know that the work done on a liquid entering the tube is given as, work is given as force into displacement. Force is nothing but pressure multiplied by the area, and the velocity V1. Now similarly, the work done at the end Y, which is the end where the liquid is leaving, will be given as P2 into A2 into V2. Pressure into area into the velocity at the end 2. Now the net work done on the liquid is nothing but final work done minus initial work done. So final work done is it's P1 A1 V1 minus P2 A2 V2. Now from the principle of continuity, we know that A1 V1 is equal to A2 V2. That is, it is a constant. So we write it as mass upon density m upon rho. So the net work done, this equation P1 you can see it here. This equation is P1 A1 V1 minus P2 A2 V2. Here what we can do is we can take A1 V1 and A2 V2 common, as we have seen that A1 V1 is equal to A2 V2 is equal to m upon rho, that is the density. So what we do is we write here P1 minus P2, and we have A1 V1 or A2 V2, whatever. So this part can be substituted as m upon rho. That's what we have it here. The net work done on the liquid is P1 minus P2 m upon rho. Now the kinetic energy of the liquid is half m V1 square, and at the end y will be half m V2 square. So increase in kinetic energy of the liquid is half m V2 square minus V1 square. This is final kinetic energy minus initial kinetic energy. Now similarly we calculate the potential energy of the liquid. So at the end x the height is h1, and at the end y the height is h2. So again the decrease or the total potential energy of the liquid will be mgh1 minus mgh2. So the net increase in the energy of the liquid is kinetic energy minus the potential energy. So that is half m V2 square minus V1 square minus mg h1 minus h2. So the increase in energy is because of the work done on the liquid. So the work done is equal to increase in energy. So we combine equation 2, this equation, and equation 3. So combining equation 2 and 3, we have P1 minus P2 m upon rho is equal to half m V2 square minus V1 square minus mg h1 minus h2. Now from here m can be taken common. We can write it here. We have P1 minus P2 m upon rho is equal to half m V2 square minus V1 square minus mg h1 minus h2. So left hand side remains as it is, that is P1 minus P2 m upon rho is equal to we can take m common, so we will have half V2 square minus V1 square minus g, because m we have taken common, h1 minus h2. So m and m cancels out, and we have P1 minus P2. We cross multiply this rho on the other side. So then we have half rho V2 square minus V1 square minus rho g h1 minus h2. So what we see is here we have two types of terms. One is containing the subscript 1, that is these terms, all these, that is P1, then V1 and H1, they are all related to the terminal X, and the terms containing the subscript 2, that is P2, V2 and H2, they are all terms related to the terminal Y. So if we simplify it, then we will, and we bring it together, all the terms containing 1 on one side and all the terms containing subscript 2 on the other side, then we will have P1 plus half rho V1 square plus rho g h1. We are simply multiplying the terms inside. Then we are bringing all the terms containing 1 on the left hand side, and we are taking all the terms containing 2 on the other side. So we'll have P2 half rho V2 square plus rho G H2. Now what we can write it as P, that is pressure energy, plus half rho V square, that is the kinetic energy, plus rho GH, that is the potential energy, is a constant. And this proves our Bernoulli's theorem or Bernoulli's principle. Now the Bernoulli's principle or Bernoulli's theorem finds a wide application in our day-to-day life. For example, if we check the design of the wings of an aeroplane, it has been made keeping in mind the Bernoulli's principle. We all might have traveled using an aeroplane, but what we do not know is it is designed in such a manner that the wings of the aeroplane uses Bernoulli's principle. Now we know that according to Bernoulli's principle, for a flowing fluid or liquid or gas, what happens is if velocity is increased, the pressure will be decreased. And it is also true vice versa. That is, if pressure is decreased, velocity will be increased. One increases, the other decreases. So here we see that in shaping the wings of an aeroplane, the outer wing has got a larger curved area. So the velocity of the wind will be higher to cover this distance compared to the velocity at the lower side or the part which is not in front. So this side they have to cover, the air has to cover a smaller area as compared to the front part. So the velocity is higher or velocity is increased. So automatically if the velocity is increased here, then the pressure will be decreased. And since in the lower part the pressure, the velocity is less compared to the front part, so pressure will be more. So what happens is the velocity of air, that is here V1 at the upper surface, is larger than the velocity V2 at the lower surface. Now because of this pressure difference, the aeroplane receives the necessary lifting force, and that's how Bernoulli's principle is used for flying a plane. Now same Bernoulli's principle is also used in cricket, where you might have heard the word called swing of the ball, and this is known as the Magnus effect. What happens is when the ball, which is having a very high speed, covers a distance, then the air around the ball also acquires a velocity with the ball. That is, here you can see that ball is rotating, and the air around the ball, very near to the ball, they have acquired velocity u. Now the air in front of the ball rushes to fill in the gap which has been created from where the ball has just passed. So from relative velocity, here for the upper portion it becomes v minus u, that is the velocity of the air above the ball becomes v minus u, and below the ball it will be v plus u. Now the velocity of the air above the ball is reduced and below it is increased. So again, according to the Bernoulli's theorem, here the pressure is less, so the velocity is less, so pressure will be more, and here velocity is more, so pressure will be less. Now this pressure difference exerts the force on the ball, due to which it moves along a curved path. Now this is the Magnus effect. Also we get heart attack because of this phenomenon only. Of course, there are biological factors as well, but what we know is we have the artery which supplies heart to the which supplies blood to the heart, and here the plaques might get deposited, which makes the area smaller for the blood to be pushed in. Now what happens is, we know that area into velocity is a constant, so automatically here the area is reduced, so velocity will increase. Once the velocity increases, then what happens is the blood pressure lowers down because of the increased velocity of the blood. Now as a result of this decrease in blood pressure, now the artery collapses due to the external pressure. Now this leads to, or we should say this may lead to, heart attack. Again, this is an application of Bernoulli's principle only. Now we will do a derivation to find the velocity of efflux of a liquid. So here we see that we have a liquid of height h, which, and at a distance, that is at height small h, we have a small opening and we allow the liquid or the water to come out, and we will see what is the velocity, what is the time taken, and how much distance will it cover. So we have the atmospheric pressure on this liquid as P, rho is the density of the liquid, and V is the velocity of efflux. Then as per the Bernoulli's theorem, we have the pressure energy plus kinetic energy plus the potential energy. So when the liquid is inside, that is the liquid is at rest, so we do not have the kinetic energy in the liquid. All the energy which is stored there is potential. So we have the pressure energy plus kinetic, there is no kinetic energy, so we write it as 0, plus the potential energy is equal to, now we equate it to the energy here at this point. So that is, the atmospheric pressure is there, that is P, plus here the energy from potential energy, it has already been started to convert into kinetic energy, that is P plus half rho V square, that is the kinetic energy portion, plus rho G into the height, and height is nothing but the total height, that is h, minus this height, that is small h. So we have h minus h. So pressure and pressure cancels out. We have half rho V square is equal to rho G h. First we'll simplify this. We'll get rho G capital H minus rho G small h. So rho G capital H and rho G capital H will cancel out, and we will be left with rho G small h. So from here, rho and rho will also cancel out. 2 is multiplied on the other side. We will get V square is equal to 2GH. So automatically V will be equal to root over 2GH. Now this is the velocity of efflux of a liquid from an orifice, and it is equal to the velocity which the liquid acquires in freely falling from the free surface of the liquid. Now let's say that the liquid assumes a parabolic path after falling from here. So we will use the formula according to the distance formula, that is S equal to half ET square. Distance here is h, this is the distance, so that this distance is nothing but the full distance minus the upper distance, that is h minus h. So instead of S we are writing h minus h is equal to half gt square. Now to find out t, it will be 2 will be multiplied this side, g will be divided, and since this is square, so we will have a root. So this is the time and time is equal to root over 2 h minus h upon g. Now if we have to find out the distance covered, this distance x, then we know that x is equal to horizontal velocity multiplied by time. So v into t. We have already calculated the value of v here. V is equal to root over 2 gh, and we have calculated the value of time, that is root over 2 h minus h upon g. So when we multiply it, we find it to be equal to 2 root over h minus h. Now this g and g cancels out, and we have only 2h into h minus h, and since we have two 2's, so 1 2 comes out of the square root. Now to find out the maximum range, what will be the maximum distance covered by this liquid which is coming out, what we will do is we will differentiate it, ddh of h into h minus h, and that is equal to 0. So this part I'll show it to you here. We have ddh of h into h minus h is equal to 0. So now first we multiply this h inside, and we have ddh of h into h minus h square is equal to 0. So ddh of this h comes out, cannot be integrated because we are integrating it with respect to small h, into h minus ddh of h square is equal to 0. So here ddh of h is nothing but 1 minus ddh of h square is 2h equal to 0. So now we find that h is equal to 2h, or this height for maximum distance should be h upon 2. That is, to cover the maximum distance, this orifice should be exactly in the middle of the tumbler, that is, it should be exactly at the half of this height, and the maximum distance that it is going to cover is x max is nothing but, we have the equation h into h minus h. So we substitute this value here, so we get root over, instead of this h we have h upon 2 multiplied by h minus this h also we substitute it as h upon 2, so we have h upon 2. Here we take LCM and we have 2h minus h upon 2. So 2h minus h is h into h is h square, and 2 into 2 is 4. So, and we have a 2 here. So now this 4, when it comes out of the square root, it becomes 2 into h square and root cancel out, so we have h, and 4 becomes 2, so 2 and 2 cancel out. So what is the maximum distance that it is going to cover? X maximum is the height of this height is the maximum distance it is going to cover. And that's all in this AV. Thank you for watching.